Login accepted.
All right. Good morning. I'm Jessica Kerr. Thank you for coming. Thank you for coming to this conference. Conferences are funny things. They're really useful because there's so many things to learn as developers. There's so much to cram into our heads. Some of this is our latest JavaScript framework and the depths of memory allocation in our runtime, and how our infrastructure works and what the heck Kubernetes did today. There's a lot of technical stuff to know. And then on top of that, there's like all these other paradigms and movements and ways of thinking, and there's like this software architecture stuff, and then there's like agile things and functional programming and OO, and there's so much that we could learn. And we get a smattering of this at the conference. But I want to consider that, like, okay, here's a bunch of movements and paradigms and things that I've learned about, some of them yesterday, some of them years ago. But what's a developer to do? What is the most important thing to learn? The most important thing to spend our precious brain power on? In this talk, I'm going to go through these 18 concepts or whatever and pull some commonalities out from them. And from that derive 3 principles that are like at the root of a lot of this. And from that, a single movement that I think underlies a lot of them. But that's still too much. I'm going to get it down to this single core principle at the center of that single movement that's at the center of a lot of this. And then at the very end, it gets weird because I can kind of explain why that principle is so important and powerful. Okay. Let's start with event-driven architecture because that's definitely been a theme at this conference. There's a lot of talks about events and event sourcing. I notice 2 important things that this does. So event-driven architecture says that when you want to communicate between different modules in your system, one system emits some events, and then other systems are allowed to notice those. But they're immutable events, and the system over here on the left, maybe that's the order-taking system, and this other one is the payment system, and you can notice those events, but you can't like change the data on them. Part of the value here is that we're reifying what happened. We're thinking first about what happens instead of what we store, what is, Tim said yesterday. But an important bit is the boundaries. A lot of what we do in software is create boundaries and divide things up and make new ways to communicate between them very explicitly. And there's boundaries in 2 senses. There's the boundaries of what can change, like what code can change, how the software can change, what can we deploy separately and safely. And then there's the boundaries of how the data can change. So our application data, our operational data, what can change in order? Not the payment system. Payment system can find out about them, but if it wants to make a change in the order, it had better talk to the order service or whatever it's called. All right, and MicroServices, same thing, also a theme, also about boundaries. In this case, specifically the boundaries of deployable units. And also these microservices, as compared to a monolith, really enforces those boundaries. You cannot call a method on a class deep inside a module that's running in another process, probably in another data center, who knows. The microservices are about enforcing boundaries and giving you the freedom to deploy and hopefully not affect very much. But when you want to refactor those boundaries, ouch. And then Neil called this out this morning. Microservices have a focus on each microservice owns its data. It owns its operational data. So there's that boundary of data change thing again. And this distinguishes it from service-oriented architecture. When I started coding in like 99, service-oriented architecture became hot pretty soon. And so a few years later, we had to divide our teams into separate applications that were each services, which all called through to the same database, which is like having 6 different mouths but one stomach. It all gets mixed up. Microservices don't do that. They say, I own the data, and you can call me if you want to change it. So that's a theme. The scoping of data change, we're really careful with that now. But the boundaries, where do we put the boundaries? And to talk about where those boundaries belong, I want to do Wardley mapping. How many people have looked at Wardley mapping before? I think everyone who raised their hand is in the front row. Cool. Wardley mapping is a fairly new movement in software and business strategy, but a lot of that is software these days. And so I'll give you about 5 minutes on Wardley mapping. It starts with a value chain map. So here we've got a customer, this little tooth person up here, and let's see, let me draw. And what does the customer need? Okay. This domain, this imaginary business is a shipping company. They handle shipping of containers, like the big things that go on trucks and boats and trains. And if somebody wants to ship a container, then they need to call in or go to the website. They need some customer support. And that customer support is going to want to give them an itinerary or maybe tell them where the container is. So they need itinerary tracking. And part of itinerary tracking is creating itineraries. So that needs routing. Now, routing in this case is finding the cheapest or fastest way to get a container from, I don't know, from Gdansk to Rome. And should that go through Krakow, or maybe it can go through Lyon? I don't know. The point is that somewhere we've got a graph of all the possible trains or boats we could put this container on, and it's our company's special sauce that we're really efficient. We have good algorithms for finding the fastest or cheapest route. And so that uses graph traversal. It needs to know how to do that. Let's see, we maybe need to know about container capacity and the properties of the containers themselves. Customer support also needs some invoicing. And of course, everything needs a database. This is fine. Not the same database. They just need the capability of storing data in a database. So the trick with Wardley mapping, and it's kind of arbitrary, like what level of detail you go to, it depends on your needs at the time, but it breaks down the customer's needs into capabilities, and then the capabilities that these capabilities need, and so on downward. And that thinking of a breakdown in terms of capabilities is a theme that I also see. Oh, come here, do this thing. There we go. In another recent movement, projects to products. And I've observed, in the US anyway, that this is kind of the next big thing after Agile that they're going to impose on us. Capital A, Agile, I'm talking about there. But project to products, I think is really cool, partly because it starts with budgets. The difference between a project team and a product team is that product teams are ongoing concerns. They're funded as a team, and their budget extends over years. Whereas a project team is funded for a specific defined package of work, for a pile of requirements or whatever. And then the project ends and the team disbands into the pool, and the software sucks. It just sucks, okay? Because the first release is never good, because those requirements that we came up with the beginning are never what we really need. Whereas a product gets better over time, because this recognizes that software is an ongoing concern. There is no done except out of production. Right, so product teams supply capabilities. Project teams add features. Doesn't matter whether those features are useful or good, that it was in the requirements, you add them and you get paid. And product teams support their own code and check on how it's doing. So these are the ideals anyway. But the product teams are supplying capabilities to the business, ongoing capabilities that we can improve. And then if we can make the software really easy to maintain and everybody's happy with it, then our team can work on supplying new capabilities, which does sometimes involve adding features. But it's adding features in order to better support capabilities or to support more capabilities. Not in its own right, that's enough, we're done, go home. Okay, so this part where teams supply capabilities, I think teaches us something about where the boundaries are. There's this really good explanation of this in the book Team Topologies. I love this book because it's like super practical. The product teams here are called stream-aligned teams, and that's like all the teams assigned to the capabilities in the Wardley maps. They are delivering value that delivers value that delivers value to a customer. And then you might also have some specialized teams, like the routing team might be a complicated subsystem team that's very specialized. There's probably a platform team that helps everybody operate their software so that you don't have to know everything about Kubernetes, because that is a full-time job in itself. Team Topologies, my favorite thing about this book, there's a lot of books in this presentation. This is a particularly nice one and easy to read. Talks about how cognitive overload is the point of breaking stuff up. The most efficient way to write software is alone. When you write your own software for your own purposes and you know the whole thing and you can change the whole thing, it's so fast, it's really satisfying and fun. This is what side projects are for. But it's very limiting in how big it can get, in the capabilities that it can offer when a single person is maintaining it. Also, it's not resilient because only one person can fix it. So we start building up teams, and then there's a limit to the cognitive load to how much a single team can know. We need to know about the technologies that we're building on, but more crucially, we need to know about the capability that we're providing. And every capability within the business is a little different. So that customer service thing is thinking in terms of customer service team is thinking in terms of itineraries, and they just care what towns an itinerary goes through. This one's going from Gdansk to Paris to Prague to Rome. Yeah, that's not very plausible, but it's fine. Whereas the itinerary tracking team thinks of these things in more detail. Okay, there's an itinerary, and it's connected because everywhere the cargo goes, it has somewhere else to go from there until it gets to the destination. And it's made of legs, and each leg includes a voyage on a train in this case, or maybe a boat. And they think about this in more detail, and they have their own concepts. The routing team has to know how to get that out of a graph, and how to get the possible voyages into the graph. Each team has a particular area of the business domain that it needs to know really well. And when that gets complicated, then you need another team and a defined interface between them. So I think that's where the boundaries are on different capabilities. So the capabilities that the business needs and that those capabilities needs break down. Each one has its own team and deployable units if it's going to be, I mean, ideally, so it can control its rate of software change. And of course, each of those domains is controlling the change in its operational data. So we have, oh, come here, let me draw, do it. Customer support talks to invoicing, and it talks to itinerary tracking, which talks to routing and graph traversal. So we've got both understanding graph traversal and understanding routing, like the translation of voyages into the graph and stuff, on the same team here. And if one of those gets more complicated, maybe they'll have to split. And then the lines here, just like microservices, because we're sending stuff over the network, we have to be careful on defining our API and careful how we change it. Event-driven architecture, I think, pushes us to be even more careful about how we define things and how we change things and versioning and stuff like that. The way these teams talk to each other is important because each team here has its own vocabulary, its own understanding of the domain. And Neil talked about this today when he talked about there may be a customer in all these different systems, but every system cares about different aspects of a customer. We all model the customer differently. So routing might model a cargo as whatever, it's a container, it has an ID. Itinerary tracking might model a cargo in terms of weight. Or maybe they care about whether it has toxic chemicals in it. Routing probably cares about that too, but invoicing doesn't. So each domain here, each capability can have its own vocabulary, which brings up the question, how do they talk to each other? In whose language, whose vocabulary do they talk to each other? And that gets into, okay, let's see. Customer support maybe has its own way of requesting itineraries, and itinerary tracking maybe listens to that. And then the customer support becomes, give me this pen, upstream, and itinerary tracking downstream in terms of who determines the interface. But maybe routing sends itinerary tracking whatever it wants. There's something interesting here in when you think about who controls the interface. This is not necessarily upstream, downstream in terms of data flow. This is a power relationship, which okay, most of y'all probably didn't get a lot of pressure to learn about feminism and feminist thought, but as a woman in tech, I do have to know something. And my friends who are experts in this point out that a lot of feminism is about acknowledging power differentials. Always look at the power differential because it tells you something about what's going on. And that happens here too, because maybe the routing, that's the magic service here. This is our special sauce. This is the stuff that's important to our business. And we need to be able to change it and update it and grow it. Needs to talk to itinerary tracking, which is the legacy system. This is the big mainframe code that no one wants to change. Now, you'd think that the most important to our business system would have a higher status and be able to tell the mainframe what to do. But I think we all know better than that. If you have a legacy system, you give it what it needs. And you're happy with what you get back because the routing, the magic service over here can change faster. It has less power in this relationship. Because if you want to get something done, you change the one you can change, not the one you're terrified of. So that's an interesting way to think about the languages in which we speak to each other. And in this case, the magic service here has implemented an anti-corruption layer a special translation layer of, okay, I have to talk to Blotus in Blotus speak and the way it understands itineraries, and I'm going to give it what it wants. But internally, I need to speak the language of graphs and nodes and edges. And so I'm just going to translate that. And that's extra effort, but it keeps the important part free to change. Because some parts of our system are more important than others, important specifically to the business strategy. And now we get back to the Wardley map, and here's the other half of it. The vertical axis is how close to the customer are you. The horizontal axis is how standard is this. So let me bring this guy up. Come here. No, come here. Come here. Give it to me. Oh, man. Come on, Miro, do the thing. I got it. All right. So the horizontal axis is how standard is it. Database, buy it as a service. Run it yourself if you have to, but for heaven's sake, don't write your own database. So that's all the way to the left at utility. This is established. Then there's other things like graph traversal. You're gonna implement it yourself, but don't invent your algorithms. Somebody has written their doctoral dissertation on exactly what you need. Go find that. This is well studied. Invoicing, get it off the shelf. You're gonna be better off conforming to someone's invoicing system when they know invoicing really well than trying to invent your own. In the middle is the custom software, and this is all the supporting stuff that we need. We just need it to do our business. Now, some of it just has to work well enough, but we need to control the rate of change, which is why we spend millions of dollars every year on developers for custom software. But then there's some stuff that you want to iterate on really quickly. Over here in Genesis, this is our routing. So like the translation of available voyages and trains and boats and things, turning that into a graph, and then using someone else's dissertation for the graph traversal algorithm. That's our special sauce, so that we need to change quickly. And that's where our best people need to be. Not on the platform team. As a developer, it's really tempting to just go deeper into the technical abstractions, because that's really satisfying because we can know about it. And that's probably great for your career if your career is going to involve like moving around and just going deeper technically. But if you want to be valuable to the company you work for, that's when you want to be on the core domain team, and you want to be understanding that language and vocabulary really well. Okay, so we've got Wardley mapping, we've got teams broken down into capabilities, and they have their own vocabulary, their own language, but not like grammar, just careful definitions of words. Because, projector mode. There we go. Yesterday or the other day, Tim mentioned data mesh, so I went and looked that up, and yes, I like it a lot. So a data mesh says, all right, you think you need a data lake or a data warehouse, and you're just gonna dump all these bytes in there, and somebody's gonna figure out how to make meaning out of that? No, there's no meaning in those bytes. The meaning requires the knowledge of a team that understands it, the product team. So make data a publication of the product team, of the domain team that's supporting the capability, that really understands itineraries or routing or orders or payments or whatever it is. Let them publish the data as a product. And again, a product is something that continually gets better. A product is something you might actually want to use, as opposed to that project, which is, well, it's physically possible for you to fill out your timesheet in this, and we can make you. So the data belongs to the team that understands it and can assign meaning. This is also crucial to writing secure code. Security has been a theme at this conference as well. So secure code, the number 2 thing you can do is understand your data. Understand the input that you're accepting and the meaning of it, and then you know how to validate it. Then you know how long is reasonable. Is it reasonable to have like pointy braces and ampersands and curlies in there? Understanding your data is number 2 thing for security. The number 1 thing for the record is upgrade your libraries. Do that first. But we can't both support what people need from our software and prevent everything we don't want people from doing with our software until we really understand what they need, including the edge cases and the weird ones. And when we do that, we mitigate one of the hardest problems in computer science. So naming, this tweet says, software developer choosing a good name for a method or variable, and he's very, very thinky. Naming is hard because we try to do it in the middle of coding. We get to that variable name and we're like, oh, what's this thing? I don't know, the container of interest. Is it a container? Is it a cargo? What are we talking about here? When we move naming, definition of our vocabulary or our language, and our mental model of how all of this fits together, when we move that to a separate activity, then we know when we get to the code what this should be called. And we can remind each other when we're in the pair, and we can get really specific about what we're talking about because we've thought about the naming first. And then we can enforce things like design by contract helps us know what a particular piece of code will not do. So an invariant is typically something that throws an exception if the data is not okay. So if we have an itinerary and we're trying to construct an itinerary and it's not connected, it goes from Gdansk to Paris and then from Krakow to Rome, No, we want to understand that an itinerary is something that a container could actually follow. So we might throw an exception. And these kind of invariants let the rest of the code assume it's going to work. And how do you find out about your data? And how do you find out about what it should and shouldn't do so that we can put these safety checks in? Well, you gotta talk to the business experts. You talk to the people who know about shipping, who know about payments. They do exist. They're in your company. They are not your customers. They are resources to the team because they are the experts in the domain and they can teach you how this capability really works. And this goes all the way back to extreme programming, also known as small a agile. The idea that we need to bring the people who understand what the software should do together with the people who can make the computer do the thing. Because in the end, we've got to get both of that understanding, that technical understanding of how to make it work, and what the heck we're trying to do and why in the same brain, your brain. So we have to talk about it. Test-driven development is another part of XP, of extreme programming. And what's important to me about this is that it forces you to think about what you're trying to do before you write the code to do it. It also gives you the experience of the caller of the code, so you have to experience the API before you implement it, and that makes it better. And then it helps to go further and bring those business experts into the testing, and that's behavior-driven design, where we get concrete examples from the business people, and then we encode them in a way that's executable to test our code. This is fun, because then when you really get down to the nitty-gritty, one of the experts will be like, okay, and we'll make sure that an itinerary always connects at every point in time. You never like make a jump from Paris to Krakow. And somebody will say, well, unless the cargo turns up in Krakow. You'll be like, what? And they'll be like, oh yeah, sometimes stuff gets on the wrong train and you gotta reroute it from where it is. And you'll be like, whoa, okay, we better change the code to express that. And that comes out, these concrete examples come out in behavior-driven design, which is useful. So this is the third principle, I think. The language, our vocabulary, and the model, how the relationships between the itineraries and the legs and the cargoes, this is crafted and shared by the domain experts and the developers, the whole team, designers too, and we put it in the code. And this is the tricky bit. This is how we make the code an asset instead of a burden. I mean, you talk about lines of code are inventory, they are a liability. We don't want our software to get huge because we need to understand what's going on. Software and the process of putting something in code has the amazing power of forcing us to really understand what we're doing, especially if you have like strong types and you're using them carefully, and you can enforce that this stuff really fits together, even more strongly than when we write stuff down, which is a stronger enforcement of consistency than when we talk out loud, which is stronger than just thinking about it in our heads. Coding, I mean, it's like math this way. It enforces some rigor. And the fun part is that when you're doing this together and you're encoding these rules and these names very carefully and consistently, and noticing when you hit a condition that's hard to test for or hard to name. When you hit something that's hard to name, that's a clue. You've discovered a concept that you collectively as a team, you go back and craft the language and model and be like, oh, I've discovered that there's an exceptional itinerary that's not connected. And so then you can actually teach the business experts a little bit more about their domain and push them to a deeper level of knowledge, which is kind of cool. But in order to do that, we need some of these other things. Object-oriented programming helps with this. Now, I started out in OO, and then I went to functional, and I got to a point where I was like, why do people use objects? But actually, I've come back around because that encapsulation really helps with a careful scoping of change. At the top level, at the object that's part of the public API, you can request the data change, and it can have all these little sub-objects, and it can enforce invariants, and it can control change. And that's really important because change is what makes everything interesting. But then functional programming is also important too, because like when you've got that payment system that can't mess with the orders, it's going to have information about those orders, but that's immutable. And immutability is a beautiful invariant that just makes everything easier because there's so much less you can screw up. And then when you get deeper into functional programming and you get into like the strongly typed stuff, and this red book basically leads you to the free monad, which is a really category theory deep way of saying make decisions separately from implementing them. And the free monad forces you to do that because it won't do any I/O until after I forgot the word for you run it, but you build up a bunch of decisions. We need to separate making business decisions from implementing them, and that's really helpful because our business logic needs to make the decision, and then we're going to get to the technical details of how we carry it out. And we separate those using hexagonal architecture, also known as ports and adapters, but because the 6 sides doesn't matter. What matters is that it's more than 2. In a layered architecture, you only have 2 interfaces. Hexagonal recognizes that there are many, although it's fine. It could be a nonagon. That would be cool. the point is you have the domain code that uses our careful names, that makes decisions, enforces invariants, and then the outward interfaces like to the database and to the other services that you need to do a translation to is outside of that. And it makes our domain code small and highly testable and very expressive. And then Neil mentioned sidecars today, so I put them on the slide. You can worry about things like the circuit breakers and being polite and networking and stuff like that in sidecars. Separate process bonus. So a lot of our architecture principles are really about letting you separate your domain code from implementation so your domain code can be functional and fully tested. Functional in the sense of not having side effects, even if it's implemented in objects. But we do have to care about those other things. We have to operate our code in the product team. And that's what DevOps is about. It's about smooshing dev and ops together so that we can suffer the consequences that happen in production of whatever we've coded. And observability is the positive side of that. Observability, as distinct from monitoring, well-implemented observability, you emit events that you get to see later for the important stuff to your domain. Well-implemented observability, yeah, it tells you about the generic stuff, the traces of requests coming in and going out, so you can worry about those non-functionals, and it fits your specific domain interesting events in there. But DevOps as a whole is about recognizing that the team that's implementing the capability is a socio-technical system. We matter, the code matters, and we need to learn from the code, and vice versa. Also, it's also about automating your ops and infrastructure as code, but the part I care about is what, as a developer, I get, which is that ability to learn. All of these three principles and the socio-technical systems and the focus on learning the domain and what our software is doing are expressed in domain-driven design. So this is the one movement that I think a lot of these others derive from. I mean, some of them explicitly. Event-driven architecture explicitly derives from domain-driven design. Data mesh explicitly derives from this. Neil talked about it today in a couple aspects. So the bad, if you're only going to study one movement, I would go with domain-driven design. It lasts forever. However, this blue book, as pictured, is like a lot of pages, and it's really long. And you're not, I'm not asking you to go read it. Instead, let's talk about what is the core principle of domain-driven design. And it's this one. It's the one about the language. I mean, a lot of things come out of this, like the capabilities. And of course, they're called bounded contexts in domain-driven design, and specifically bounded by language. But that language is the most important part. So the one thing that you can do to improve your software and get specifically more valuable as a developer is to learn that domain and be specific with your language. This is especially fun as a new employee. I just started at Honeycomb this month, and I get to do the thing of making people be really specific about what they're talking about. Okay, when you talk about OpenTelemetry, is this a library? Is it a process? And they're like, oh, it's a distribution. What the heck is a distribution? And when we talk about that, so I get these words, and they're like, okay, all right, we'll call it, it's really the Honeycomb's OpenTelemetry distribution for Java. And so that's so long that we call it a bistro internally, but you gotta make people be really specific with their language. Unfortunately, my team is nice and appreciates this. When you notice that people are using words in different ways, let's unify on exactly what this means. Let's be precise and define this language carefully. What is an itinerary? Does it have legs or stops or destinations? narrow in on a word, especially when you're new is the best time to do this. So that shared language, and it's shared among the whole team, the code, and also these domain experts that we brought in, is the superpower of domain-driven design, which in turn is a power behind a lot of the other movements and paradigms that we use. And so now it gets weird. I have 10 more minutes. You can deal with 10 minutes of philosophy, I promise. But this is why that shared language is so powerful. So as people, and here's our socio-technical system of software developers and the code, which impacts the world of the users. And here in the little thought bubble is the shared model, including that vocabulary and how the pieces fit together and what that means for the capability that we're giving to the users. Sharing that model lets us build this system, lets us work smoothly together and implement it correctly and well and usefully. But sharing that model is hard. The model, to be specific, the model in domain-driven design is something that lives in our heads, in our collective heads. There's like a UML diagram somewhere, and that's useful for helping us get our model consistent. And it's in the code. That's one representation of the model, which is great because it's executable and really helps us get it consistent. You might write a glossary with your vocabulary terms. That is not the model. It is one representation that helps us get it consistent. But the real superpower of our software team comes from getting that together. Okay, here's my favorite philosopher, Karl Popper, and his explanation of this. That model that lives in our head is a real thing, but it's not a physical thing. I mean, a cargo in a container it represents some physical thing. It refers to a physical thing. But an itinerary? We made that up, but it's a useful concept. Okay, so world one is the physical world, the actual container and the stuff and the trains exist in world one. Popper's world two is individual experiences, feelings. We live in this world of our own internal experience and feelings, but we can't communicate it to anyone else. It exists only internally. World three is the world of objects that we can share, the mental objects that we can share with each other and communicate, starting with language. And the thing about world three is that these things are real. You can tell they're real because they're causal. Take money, for instance. It's confusing sometimes to think about how money is so important in our world, and yet it's really imaginary, right? I mean, yeah, there's cash, but that only has value because we've invented this concept of money. Yes, we invented it, and it's real. That model that we have in our head is real, and it's causal, and it affects how we make the code, and the code affects how the users can work. It's a real thing, and it's valuable. And it manifests in world one, in the real physical world, on the screen, for instance, if this is a website or a client, because the people using our software, it changes their physical world. Depending on what you see in Google ads and in Facebook posts, you live in a different physical world than maybe someone next door who sees different ads. We really do live in different worlds. Okay. And this feeds into our products because what is in our head determines how much value we can give to the people using our software. Cesar Hidalgo, here's another book, is a statistical physicist, and he has this book, Why Information Grows, which defines a product as embodied knowledge. So if I have this clicker, then I have the capability of advancing this slide from over here without knowing anything about radio transmissions or whatever the heck it's using. Maybe it's Bluetooth. I don't have to know about that because this thing does. The knowledge is embodied in the product. And in software, the knowledge of how to do that thing, that capability that we're providing, is embodied in the running software. And that is valuable because people can now ship their containers without knowing anything about trains between Paris and Rome. We let people do things that they couldn't before by encapsulating knowledge. And that this is the software embodying the model. So we put the model contains the knowledge, and then we put that in the software, and then people have it and they can use it. The thing is that the challenge here is that these World 3 objects, including the models and this knowledge that we have, doesn't transfer magically from person to person. If I hand you this clicker, you have this clicker. But if I tell you about observability, you have some concept a little bit, but it rarely matches. The exception is math. Math is World 3 objects that we have discovered. Some of them we invented, and then we like numbers, and then we've discovered all their properties and things and more exciting mathematical concepts that we then notice in nature. Math is defined entirely in World 3, and therefore it can be so precise. There's no ambiguity because there's no direct reference to the physical world, that we really can transfer it fully. And this is another reason that we try to make our code reason aboutable, more mathematical, because it does that precision of model can transfer better. But then somewhere you have to hook it up to the real world. Right. So so we try to make it more mathematical. We put it in the code, but then we have different mental models in the different contexts because there's only so much we can know. There's only so much knowledge we can put in each one. And this is crucial, actually, because the boundaries, they're called bounded contexts for a reason. And these boundaries here are what make it possible to have precise definitions. Math is very bounded. I mean, when you define a set or a group in category theory, it's like, words are escaping me. It's very specific about what it has. It has this operator and that operator, and then you can have a semi-group by removing that requirement, very specific. We can only be that specific within a specific context. And that's why we need these boundaries between the team. Here's Popper again, except much younger. He noticed at 16 that his intellectual father and friends would argue over definitions. And Carl recognized he's like, why do they do that? That's pointless. The meaning of a word is in its use. Arguing over global definitions, you and I can argue over what observability means. Whatever, you're going to do your thing and I'm going to do my thing. However, within a team, agreeing on definitions is priceless. That makes us able to move together. That makes us able to build something bigger and more useful than a single person could. And then, as software developers, we have the particular power of also agreeing on those definitions within the code. And that makes our knowledge real and accessible to people. There they are, the people. And this is why software development is reality construction. Neil said it today. For better or worse these days, software defines everyone's reality. When we build this knowledge and we put it into a product that in one way or another physically manifests for people, we're building their reality. That timesheet program that's incredibly painful that you have to use every day, somebody built that reality for you. A product team gets to continually refine and improve our reality, and we get to craft the language that we use to express the knowledge that we put into the software that defines the reality. This is our superpower. This kind of crafting of languages, building it together more broadly than software, is called participatory sense making. This is what we do with the domain experts, and the code can help us too, help us with rigor, to make sense of the world. But when we're doing this in software, we do more than make sense of the world. We make the world. We can make it more meaningful to us, and we can make it more useful, and we can make people's world a little better, or we can make that timesheet project and make everyone's world a little worse. Go, go. Okay, don't go. And that's when we build our semathesy, our socio-technical system of people and software, and we all learn from each other, and we create a better reality in the world. And that's why being a developer is the most awesome thing ever. The end.